So behind us on the screen is our schematic of our project. On the left hand side we have our expansion board, and on the right hand side we have our development board, the MSP430. The MSP430 comes with an analog to digital converter, and it has two reference voltages, either 1.5 or 2.5. In our case we went with 2.5. So we knew for our V out on the expansion board we needed to be 2.5 volts. So with the basic voltage divider is how we came up with the values of 1K and 2.2K, using the voltage from the input of the PC and the battery pack, and you solve for R1. And then they each tie into a jumper with a simple switch, and we have our throttle pod, which will vary from 0 to 5K, which will give us our various voltage from 0 to 2.5 volts, which will then send that point into the analog to digital converter.
Our signal coming from the throttle pot will be fed into an analog to digital converter. In this case, the MSP430 is supplied with a 10-bit ADC, and it's set up right now for a single channel, single conversion. What's initiating this conversion is timer B. And what we have it set up to count from 0 to 100, and on an overflow it will create an interrupt. And when that interrupt is initiated, an interrupt service routine will run, and it will initiate a sample on the ADC. Once the sample is taken, it initiates another interrupt where that value is stored from the memory onto the register that controls the threshold point on another timer. This value is TACCR1. Now, timer A is our pulse width modulating timer. We have that counting from 0 to 1024, upon which it will reset. Now, our main clock is also our sub-main clock, which is running at 16 megahertz. Now, when you have that combined counting up to 1024, it creates a signal that runs at 15 kilohertz. And this is what we need for our DC motor for electric vehicles. It needs to run at about 15 kilohertz. So that's what we have set up here. Now, when this timer intersects either with the threshold value or an overflow, it'll create an interrupt, and that'll create yet another interrupt service routine. And in here, this is where we find out where that interrupt came from, whether it's the intersection point, the threshold, or an overflow. If it's an intersecting point, then we set the output high. If it's an overflow, then we clear that output. So from there, we get our pulse width modulated output, like so.
So we're going to give you a live demo of our project in action with our throttle pot hooked up with the MSP430. Right now I have it running through the hypo terminal, and you can see that it's just continuously updating with numbers. It's talking about with the timer B counting being 10 times faster than timer A. The first column here is going to be our ADC output. So right now it's basically at 0, where it's fully no power, and we'll just start to vary it. You see the numbers now are about 635. Cruise all the way up, and there's 1023, which we are wanting 1024. You can just see it just changes back and forth. So our second row of columns there is going to be our threshold voltage, and that's what I don't know if you can see it from the screen or not, but we started out at 1200 because at the top end and the bottom end it gets a little shaky, so we basically have it going from basically in the middle range to get rid of that shockiness. And what you do is you just take the 1200 and minus the ADC, and that'll give us our threshold. The second number is basically the on and off of the LED, which we'll show you here in a minute with the dimming on and off. As you can see now, we have it completely off, and it's outputting all zeros. And then as you get higher, you can see that the ones are still coming. Every so often there's still zeros, just because of the switching cycles, but it's still mainly ones when it's completely on. Okay, so we just had the lights off, trying to hopefully get the green LED to be brighter in the camera, but unfortunately it was still unable to see. So for those of you out there, you'll just have to take our word that there is a green LED and that it does work. Okay, so the next thing we want to do with our project is we want to make a wireless channel to be able to remotely send the parameters of our motor controller to say, a driver inside a vehicle, to see the voltage of the battery, current going through and the duty cycle and stuff like that. Due to, I wouldn't say a glitch, but a snag that we developed or came upon at this time, it's not going to be possible.
The communication on the SPI to the CC2500 needs to be less than 10 megahertz. And since we set our clocks to run at 16 megahertz, we'd have to dial this down. And for a simple explanation, we don't want to do this for the fact that we will essentially lose the resolution on our ADD converter. The reason being is we'd have to lower our scaling factor, or to create a scaling factor for our ADD output, which essentially, instead of there being 1,024 different slots or bins, you'd only have maybe like 250. And although that might be enough, since our final application is going to be for motor control, where safety is a big deal, we want the maximum resolution as possible. So in order to get around this, we would have to go in and create like a software delay to manually lower the communication clock to the CC2500. So this is something that we're going to continue on pursuing. Although the scope of this class is over, our senior design project is going to carry on to next semester, and this is something that we actually want to pursue. So that way we can present to our customer another product that they can sell. Of course, like we mentioned earlier, it might be a little bit more expensive, but it will add a lot more functionality, a lot more bells and whistles, a lot more tweaking. You can do a whole bunch of different things with this.
So thanks for watching our video today. Hope you guys enjoyed it. And if you'd like to follow up on our project, you can Google us at NAU Motor Systems. Should be the first link up there. We'll have this video posted, and along with the rest of the semester of our progress. Thanks a lot.
Thanks. Bye.